Welcome students for the UGC lecture series on lasers and their applications. This is under the Swayam portal. We have been having quite a few lectures in this under this umbrella of the Swayam portal. We have seen all along what are the principles and the design of lasers. That's the first step. Second step, coming to the applications of lasers, we have seen some passive applications. What we mean by passive applications is laser falls on certain object, say a cloud, then it gets reflected, scattered, all the message that come back from the cloud will carry information about the cloud. In that case, after receiving the laser beam, we will look at what kind of modifications have undergone, what kind of modification the sent laser beam has undergone. Only that are important for us. These are called the passive applications. We have seen a set of them. Now, we are going to see active applications. Active applications means laser will do something on the object. Passive applications means object will do something on the lasers. That is a major difference. In active applications, automatically it implies that we need a high power laser to do certain thing on the object. High power laser means it is much better to do lot of application with the pulse lasers, because the pulse laser can deliver enormous energy in a short duration. It will be like a punch in the wrestler. Maybe you have seen the wrestling match or the boxing match. The whole match will work only for 10 or 20 minutes, not like a cricket, it goes for days. It will be short time, very powerful, very thrilling match, because two people are going to hit each other with enormous force. That is a boxing or kickboxing or karate, whatever it is, all of them are active game. This kind of high power applications are called active applications of laser. Before we go into that, we shall now just give a broad outline. Make use of high power lasers in continuous mode or in a pulsed mode. The whole domain of material processing have been totally modified, dramatically changed by the lasers. Not only material processing, in the hospitals also variety of applications are there, where laser does something on the tissue. Already you are already familiar with that one. We will touch all those things later again. Now, what are the lasers that are really useful in this kind of active applications? Are most important highly useful lasers for industries are neodymium mag laser, high power neodymium mag laser, most often QSIT neodymium mag laser is the best one. The second best one would be high power carbon dioxide laser. This carbon dioxide laser, perhaps you may remember in our earlier lecture, it is working as a infrared laser, and that too far infrared laser. When it focuses, what you will get is a very high heat power, enormous amount of heat power can be focused on a very small spot, so that you can convert anything into a smoke. That is the beauty of carbon dioxide laser. The carbon dioxide laser is 10,600 nanometer, neodymium mag laser is 1060 nanometer. That means, the wavelength of neodymium YAG laser is 10 times less than the wavelength of CO2 laser. That is very important. Neodymium YAG laser is almost near infrared. It has another domain where neodymium YAG laser is the king. There is no comparison for this laser. This is one laboratory or one industrial application. There is another important industrial application where CO2 laser is a king. These are two important domains. Coming but in neodymium YAG laser, ordinary neodymium YAG laser comes out with a power of about 10 to 20 watt CW laser, ordinary at 1060 nanometer, ordinarily, commonly available. These are not so very expensive. On the other hand, if you have a Q-switched neodymium YAG laser, Q-switched means the pulse inside is certain way manipulated so that a large number of population inverse is built up. It is something like holding a big dam, using a big dam to allow the water to come and come and come and there get collected there. So, a big dam collects water over a period of time. After the water level has come to a high level, before the dam breaks, when you open that gate, you will see enormous number of water flow out, and that kind of water flowing with enormous power, enormous force, enormous momentum are the one very much used for hydroelectric power generation. If the water is flowing continuously, that is the best for irrigating your field. In a paddy field or plant banana field, water should flow continuously, very slowly. In power generation, hydroelectric power generation in Mysore or Pavanasam or any of these places, you need lot of water falling at a height at enormous force, so that the generator will be able to rotate the wheel, and that is how you generate electricity. These are two important way of making use of the same kind of water. In a similar fashion, we are going to use a laser also. At this point, I must say something about the coherence. We said in the previous lecture, for a passive applications, particularly we have given enormous emphasis for holography, and holography means Heine laser. They are made for each other. The coherence property of helium neon laser is very, very good. Only then it is capable of producing fringes, interference fringes of we were employing LCD, liquid crystal display, to look at our TV. Old Sony TV, we even now have it. Then next step, people went on to LED, light emitting diode, that kind of type. And then after some time, if you see, now you have got Q dot Q LED, quantum dot LEDs made of quantum dots. And before that, you could have seen organic, yes, I got the idea. They are called organic LEDs. Look up, watch out. Today if you go, you will see OLED, and next one is QLED. The difference between this and this is the resolution. If you see the picture with the QLED, you will never forget it, because it gives a very finite detail. In a similar fashion, if you want to construct a hologram, helium neon laser is the best. Now, when you want to come to active applications for material processing, helium neon laser has no use at all. Keep them under the box and shelve them in the corner of the room. They have no value at all. This active application is a domain of heavyweight champions like a CO2 laser, neodymium YAG laser, or argon ion laser, Tice-of-fire laser, these are all high power lasers. They have their own use. For them, coherence is not important. All that we need is a light should come through a small cone. Spectrally, okay. What I mean is spatial coherence also is not very important. All that I need for active applications, I must have enormous number of power coming out in a straight line. That could be straight away, use a mirror, allow it to come down and start cutting the table. That is all what I need. Or I should be able to launch in an optical fiber. Optical fiber will be usually thick, it is not so thin as we use for optical communication. A single mode fiber, very thin one, which will be able to take the message without much distortion. What is finally required is the true property of whatever we have sent. Let us take the example of a professional courier. He is supposed to bring a letter for me from somebody. He is supposed to bring the packet or the letter without he should not write anything. He should bring carefully and deliver it as it was posted there in some other place. He should not make any change in the packet that what I want to have. That is the kind of property required for optical communication. On the other hand, for material processing properties, you need high power lasers which will be able to distort, change the property of the material. In this case, the divergence is not important. You can have a divergence of 10 milliradian. Very often, the neodymium, very often the excimer laser, which is used for photorefractive keratomy, usually it will have a very good divergence of 10 milliradian. Compared, a helium-ion laser will have a divergence of 0.1 milliradian. It will be very neat, whereas this will be broad, but it carries enormous power. Now, next important point is you can have a Q-switch laser or a mode lock laser. A Q-switch laser will convert microsecond pulse into a nanosecond pulse. A mode lock technique will convert a microsecond pulse into a train of picosecond pulses. What is Q switching? What is mode locking? I hope already I have explained in my previous lectures. What we need is a train of pulse of 10 picosecond pulse duration with a repetition rate of, let us say, 10,000 pulses per second. Remember, in 1 second you will get 10,000 pulses, but the actual duration of pulse will be about 10 picosecond or 50 picosecond. That means it is again come back to the boxing of Muhammad Ali or Mike Tyson. They will just give a kick and then another kick. Look, one kick, actual the duration of the kick will be like a lightning, few fraction of a second, but then he will withdraw and give another thing. So it will take 30 seconds. Actual kick will be a fraction of a second, but the time between one boxing, one shot and another will be few seconds. Same way, in a mode lock laser, you will have a train of pulses of typically 10 picosecond, and the pulse duration between them may be about 1 millisecond. Okay, let us stop with this one. Now, for low power applications, which you have already finished, you need coherence, very important. Spectral coherence and the spatial coherence, both are very important. Only then you will be able to do very good quality hologram or very good quality optical communication. These are the two important great applications of lasers. In contrast, when you go to active applications, what you need is a very high power coming through a small aperture. It should have reasonably good spatial coherence. Temporal coherence is not very important, is good, but not very essential. What we need is enormous power coming through a small aperture. A divergence of 10 milliradian, 20 milliradian is okay. With that also we can do. Then such lasers can come as a microsecond pulse, nanosecond pulse, or a picosecond pulse. To do that, you must take some extra precautions to introduce certain kind of shutters inside the resonator cavity, so that you have a Q switching element or you have a mode locking element. These are extra additional features which have to be incorporated inside the laser. Only then you will be able to get nanosecond pulse or picosecond pulse. Next important point is, when we say nanosecond pulse, the time duration, the whole duration of a Q switch nanosecond pulse will be about 10 nanosecond, typical. Best example is my favorite neodymium laser. It takes from 0 to go to the peak 5 nanosecond. The next 5 nanosecond it will come down very fast. The total duration will be 10 nanosecond, that is all. But between two pulses, the time difference will be about 20 second, 30 second, whatever it is. What it means is, if the pulses are 10 pulses per second, that means in 10 pulses per second means between the two pulses the time duration is 100 millisecond. That is the meaning of this one. But the pulse width, the time duration of the laser pulse is only 10 nanosecond, but the sequence, the time difference between the two pulses will be about 100 millisecond. That is for the Q switch laser. In another case, for a mode locked laser, you can do mode locking with a neodymium laser also. In a mode locked laser, for example, the pulse width will be about 10 picosecond. Picosecond is 10 power minus 12 second, extremely small even. Now, the pulse duration will be 10 picosecond, but the number of pulses per second may be of the order of kilohertz or even megahertz. If it is a kilohertz, it means in 1 second you will get 1000 pulses. That means if you calculate it in 1 second, if you get 1000 pulses, the time difference will be only 0.01 second. That is the meaning of this one. But the pulse width is about 10 picosecond. You can carefully work it out. That is the property, difference the property of nanosecond pulses and Q switched nanosecond pulses, mode locked picosecond pulses. Both have different types of applications, both have different types of active applications. Now, we will go to the next step. We were able to play around on a time scale. What I am trying to bring to your mind is, we started with microsecond laser pulses, converted into nanosecond pulses, and then we were able to play around to produce picosecond pulses. We can even produce femtosecond pulses also. That is also possible. That means we play around on the time domain. Next step, can we ever play around on the frequency domain or the wavelength domain? Yes, this is called frequency converted laser. Frequency converted laser means Suppose I start with the laser of, let us say for simplicity, 600 nanometer. I can put a second harmonic generator in between, outside the laser cavity or inside the laser resonator cavity, so that what comes out will be the second harmonic or half the wavelength. This point I should re-emphasize. Unless I have a special provision, I get a laser at 600 nanometer. 600 nanometer is a beautiful orange color. It will be something like your sodium lamp. Such lasers are available. Now, if I want to have the second harmonic of this yellow color, which means second harmonic means twice the frequency or half the wavelength. That means 600 divided by 2, 300 nanometer will be the wavelength of the second harmonic that we will be able to get. That means you have to do certain type of special introductions, small certain kind of changes in the frequency of the laser. That means you have to introduce a second harmonic generator, a certain kind of special crystal which will convert the fundamental 600 nanometer into second harmonic of it, which will be 300 nanometer. This kind of crystal can be inserted inside or outside. Most often, for all many practical purpose, we keep it outside, do not put it inside. This is the common practice. Second example, second point is the 600 nanometer laser, which are possible, not so good. So, whenever I say second harmonic generation, throughout the world people will always think of 1064 nanometer neodymium laser getting converted into 532 nanometer very beautiful green neodymium laser. This is what you will find in many laboratories, many industries in India or throughout the world. This is most common. This is second harmonic. Next one, another possibility is, instead of second harmonic, I can have third harmonic also. Third harmonic means 1060 nanometer divided by 3. Third harmonic means 3 times the frequency or 1/3 of the wavelength. So, 1060 divided by 3 becomes approximately 355 nanometer, that falls in ultraviolet. Remember, ultraviolet light cannot be seen at all. Ultraviolet light can be seen only if you put a paper. If you put a paper, on the paper there are certain chemicals. Those chemicals will absorb 355, will undergo excitation and produce fluorescence. That fluorescence will be violet or bluish, usually violet or bluish in the paper. From there I know that 355 is coming. If I do not have any such paper, if I put my hand, I will see the burning in my hand, because 355 Q switch laser from neodymium will just burn your skin, and I have got the pinch so many times in many part of my skin. I would have got it by mistake. When we do experiment, it is a way of life. We are familiar with this, we know what it will do. It will burn for some time, just put water, go for a coffee, and then we continue. It's all. It is not really very harmful. It will not do any permanent change. It will burn a little, that's all. Now coming back, I don't want you to play around with this one. Unless you are an expert, don't do all this one. Coming back to this one. Now let us see how we produce second harmonic and third harmonic. This is what we mean by non-linear optics. How it is possible is something like this one. In a harmonic generation, what is important is you should be able to produce enormous number of electric field which will be able to produce certain changes in the crystalline structure temporary change in the crystalline structure. It should be capable of producing second harmonic inside the crystal. The best crystal is a KDP crystal, potassium dihydrogen phosphate. Next one is ammonium dihydrogen phosphate. These crystals are being grown in Anna University. They are all very popular and they are very good ones, and they are very common ones also. Now, these kind of crystals have certain special property of nonlinear property. Nonlinear property is possible when there is no center of symmetry. All these things you may not be able to understand from whatever I am explaining. These are essential part of crystal physics, but I want you to at least listen to such an expression so that later you can ask your teacher why second harmonic generation is possible only in few crystals like KDP or ADP, or you can try even in quartz. Calcite, all of them are capable of producing second harmonic, but the efficiency is the best with the potassium dihydrogen phosphate. Suppose I have a laser, 100 megawatt ruby laser, which is possible employing Q switching technique. Then such a crystal, such a ruby laser, the wavelength of this one is 693.4 nanometer. That is the wavelength of a ruby laser. Half of it, the wavelength will be 347. I start with 100 megawatt. Look, this is a Q switch laser, 100 megawatt, and when it falls on a suitable KDP crystal, I would be able to get 10 megawatt at 347 nanometer. This is what I will get with the ruby laser. In contrast, if I have a 100 megawatt neodymium glass laser or neodymium YAG laser with the power of 10 megawatt, I would be able to get third harmonic, which will be 353 nanometer, 353 or 354 nanometer. But only point is, when you convert it to second harmonic, the efficiency of conversion is about 10 to 20%, let us say 20%. In this example which I have shown, it is about 10% only. We start with 100 megawatt ruby laser, you end up with the second harmonic of it employing a KDP or ADP crystal. Finally, you get 347, which will be an ultraviolet laser. This is one possibility, or another possibility, you start with the 100 megawatt neodymium YAG laser, you get 353 nanometer, which is in the ultraviolet, the power will be about 10 megawatt. Now, these are the examples I have repeated so many times, because after so many years of research and application throughout the world, these are the two types of laser and these are the two types of crystal which have stood the test of time. What I mean to say, if you go to any laboratory, ask for a neodymium YAG laser, if they say we have a high power neodymium YAG laser, next question, do you have second harmonic? Do you have a third harmonic? Yes, yes. Then let us go. What kind of application we will go? You have a range of application. I always say this neodymium YAG laser is a workhorse of any laboratory, because it is a solid state laser which will not get spoiled. I have used a laser, this laser, after 10 years of anybody use. I once used in some laboratory, then after 10-15 years I did not go there. After 15 years I went there, I touched it and worked up, it said, okay, I am ready to work with you. Such a rugged laser is very, very rare. These are having enormous number of applications which we will see in the subsequent lectures.